Yes, thank you. Thank you all for having me. I'm sorry I cannot be here in person. Can you hear me well? I think so, huh?
Yes.
And the screen is fine as well? Yeah. So sorry I cannot join you over in person. Sorry, as I hear a lot of nice stories about boat trips and oysters and all that, but mostly sorry that I cannot see you guys and sit down and discuss, I don't know, morphological effects on nuclei and lysosomes in person. But luckily we can do it online. And yeah, so I prepared a presentation on a project that we did together with Andre, René, and people from Israel on the well, morphological effects of the glutamase deficiency. So this is a project that started with 3 patients from, let me see, Israel does not move. Yes, there it goes. And it had to deal with, it deals with the glutaminase. So glutaminase is an enzyme that catalyzes the hydrolysis of glutamine to glutamate, forming also ammonium. It's the most abundant amino acid in the bloodstream, so it is very important. Especially glutamate is important for various reasons in the biological process. So intestinal metabolism, but also cancer and neurodegenerative diseases. All these processes have been known to have an effect on the glutamate. So it's definitely an important enzyme to look at. Now, glutamase deficiency has been reported previously, and in a couple of patients, 13 in total, it has been described. And basically, it's an inherited metabolic disorder. Now, there's 2 types. Type 1 as either a duplication of the exon or a short tandem repeat expansion. And then the problem is that there's a global developmental delay and ataxia. The more severe mutation is in fact a frame shift or nonsense variant mutant, where thus far only 5 patients were described, and we add 3 patients to this list with this paper. The patients have more severe effects, so there's a progressive loss of brain matter, often it's lethal, already in a neonatal onset, with also respiratory insufficiency. So what do we have in this study? We have 3 infants with GLS deficiency from 2 unrelated families. And one of those families is in the scheme here. Well, you can see with all these connecting lines, there's a lot of connections in this family. And in fact, patient 1 and 2 both have first-degree cousins as parents, which is causing problems, of course. And patient 2, even the 2 grandmothers are sisters, so there is quite some close relatives in this family. The babies presented clinically with neonatal onset and both epileptic problems, respiratory failure, and progressing to either persistent vegetative state or even early death. Only 1 patient remained alive at the age of 7 years. And so I present work on patient 1 and 2. In the paper, we also have patient 1 and 3, and patient 2 is also has been studied, but we focus on 1 and 3. So patient 1 is the patient that survived for 7 years now. She's in a vegetative state, but in a stable state, so there's no frequent hospitalization necessary. She seems medically stable, although she has a lot of support. So there's mechanical ventilation, and also needs physiotherapy. She cannot really communicate, talk, and respond to input. So there's definitely problems. Patient 2 and 3 are very alike, and at birth there were a lot of problems. So also respiratory intubation was necessary, and seizures started at day 1, and both only lived for 3 or well, a little bit more than 1 month. And patient 2 died of cardiorespiratory failure, and 3 died of respiratory failure. Now the Israeli group made MRI images of these 2 patients at day 9 and after 17 months of patient 1. And then there's in the beginning, so at day 9, the brain structure is grossly normal. But at the 17 months, you start to see well, degeneration and volume loss, especially when you compare these 2. There's quite a lot of material degenerating, and obvious that things are not right. And also for patient 3, this is all these points have been found in the MRI scans. So they were able to culture fibroblasts from skin biopsies from these patients and send that to Amsterdam, where my colleagues started to biochemically characterize. So first the activity of the enzyme, and compare that to the controls. And in patient 1 and 3, there's no activity of the enzyme at all. And on Western blot, we showed that there is still protein there. Patient 1 and patient 3, the amount of protein seemed to be decreased quite a lot. And then functional analysis with stable isotopes were done. So the glutamate, glucose, and olate were both labeled, and you can follow then if it's been incorporated, and then you can see that patient 1 and 3 have very low levels, although here at this malate fraction you see there's a little bit of a compensation, but further on in this all these show impaired glutamase activity. Then some microscopy was done on the fibroblasts, showing the localization of the GLS, and compared it to mitochondria. As it's known that GLS is going to be present in the mitochondria, so those 2 were compared. And then to our surprise, we see quite some nice staining for both patient 1 and patient 3. There's quite a nice level of labeling. So then they came to us asking what is happening to these cells. Can we see any morphological effects? Now, we had some projects before with fibroblasts, and we knew that these sort of pancake cells are a little bit difficult to work with. They don't like to pellet down in a nice pellet. So we decided to compare a couple of different fixation protocols, as we had quite nice results with a more mild fixation. But to make sure that we did the right thing, we compared a couple of things. So it may be very simple, but it was very important for this project, so that's why I included it in this presentation. So what we did, we use an old method from the lab where you remove the medium and then add fixative to the cells. So this is quite tricky. If you give this protocol to an untrained person, there's always a chance that they dry in the cells, and this is very harmful for the cells, of course. So often we give the protocol to add 1-in-1 the fixative to the medium and then replace with full fixative. But yesterday we heard from Eric that combining different buffers is not a very good idea. So this might be not the right scenario. And then also we wanted to see if the FEM-based fixatives that we normally use for immuno-EM would be successful. So here there's only a little amount of glutaldehyde and 4% of paraformaldehyde. And we give it for 1 hour and then replace it with storage buffer. Or we give it for 1 hour and then replace it with the 3%. Or we replace it with the same fixatives, just to make sure that we get the fixative right. Now this is, as I said, the method that we use for the immuno-EM method. And we just had a project together with Carnebeek where we looked at fibroblasts as well. And that did the immunogold labeling with CD63 on these lysosomes, and that worked really nicely. The structure of the lysosomes was very nicely preserved. But when you stain for EPON, so when you dehydrate, we were in fact more happy with the first protocol. So the old protocol to remove the medium and then add a lot of fixative to the cells. And we also improved or changed the protocol of embedding a bit. As we had problems before, we tried a couple of things and realized we do need propylene oxide. Although, as we heard in the first day, that using this is maybe best avoided for environmental reasons. But in this case, we do need it for getting these cells in a nice pellet. Also, we use warm EPON when the pellet is disturbed, overnight incubation and very careful centrifugation. And then we get nice pellets. So this is an example of the 3%. And you see a lot of beautiful lysosomes, and the morphology of the cells is good. And when you compare that with the more mild fixation, you see that not all of these lysosomes are nicely conserved. So then we go to the results. We have a good protocol now, and we can start comparing the morphology of the control cells. So I can always show the top two, control 1 and control 2. Patient 3 is on the left and patient 1 is on the right. And then when you look at the morphology of the nucleus in the control, they look well, like this, like normal round cells. And in the patient 3, we see a little bit of fragmented invaginations of the nucleus. But in patient 1, which is the patient that survived for 7 years, the nucleus often look very, very strange, completely altered and fragmented. Then we compare the Golgi stacks. In the control, we have large sheets of Golgi nicely next to the nucleus. And both in patient 3 and in patient 1, we do see Golgi stacks, but they seem to be a little bit more fragmented, although they're very visibly present still. Then the ER is dilated in the patients, both patient 3 and patient 1. We see a swollen ER and lots of polyribosomes. So these little curls of ribosomal structures, ribosomes in little rows. You do sometimes see that also in the control, but in both the patients, we very often see this structure. Then lysosomes. In the control, we have beautiful multilamellar, or whatever you want to call them, lysosomes with lots of membrane inside. And in patient 3 and in patient 1, we see swollen lysosomes. So lots of electrolucent space. They seem to be disrupted and broken in pieces. And it's not the fixative, as I've shown you, that well, in the control, the fixation is working well, quite nicely. And also at low magnification, this becomes really clear. Large fields of open electrolucent lysosomes, whereas in the control, there's much more filled. Here we also compare it with the short tandem repeat patients that André and René have in the lab as well. So those are the patients that do have the enzyme still there, but it's not functional. And when you compare the lysosomes in these from these patients in the fibroblasts, they seem very nicely intact, and fields of those lysosomes can be easily found. And in the patients with the frameshift mutation, there's a big difference. Then we also stumbled upon glycogen accumulation. So in control cells, of course, you can always find a little bit of glycogen in the cytosol. but it's not very easy to see. But in the patient, we do find fields of glycogen, although here, as we call washed out glycogen. And in patient 1, we see also increased amounts of glycogen. And again, when we compare that with the short tandem repeats, we do see a lot of the glycogen also in that patients. And of course, the glycogen structure can be nicely compared here with the ribosomes, being a little bit bigger than the ribosomes. So when we found that the glycogen repeats, André decided to also look at these metabolic activity in the fibroblasts and look at the basal cellular oxygen consumption rates. In only patient 3, the cultures for patient 1 were no longer growing. So we only have the cell line from patient 3 for this type of analysis. And then you see that the basal respiration is a little bit more variable, but stable and the same as for the control. But the spare capacity increases a lot in patient 3. And when they looked at the ATP, it's clear that the majority of the ATP is being synthesized via glycolysis, whereas in the mitochondrial ATP, that does not really seem to change. And also the seahorse analysis shows there's an increase in glycolysis in patient 3, whereas patient so the short tandem repeat patients in red and the controls are in a different scale in the seahorse analysis. So then the last thing that we wanted to analyze, of course, was the mitochondria. This is, we were expecting to see a lot of effect in the mitochondria. And we were a little bit disappointed in the sense that, especially in patient 3, the mitochondria seem rather normal, and the cristae present, and well, they look very similar to what we find in the both control cells. In patient 1, we do see more fragmented, maybe also morphological alterations when you compare that with the controls for the mitochondria. But of course, we already knew that from the fluorescence. So when fluorescence was done on patient 1 and compared it to the control, we already knew there's quite a lot of mitochondria still present in these cells, even though this enzyme is accumulating in lysosomes, and others have shown a lot of effects on the mitochondria. So in conclusion, we can say that GLS deficiency, at least in the frame shift mutation, affects fibroblast morphology. We see nuclear fragmentation, we see glycogen accumulation. Mitochondria are present, but might be more fragmented. And we see dilated ER and polyribosomes present in these cells, and of course lysosomal swelling. So there's a broad scheme of different morphological alterations, although it could be secondary to this whole GLS deficiency. And yeah, so this work was done with together with René Kuilenberg and André Kuilenberg and René Leen from Amsterdam, and people from Israel, where these patients were analyzed, and Anita did most of the electron microscopy work. Thank you for your attention.